In this video, I'm going to explain how to draw Lewis structures. So Lewis structures are generally a way to show the covalent bonding, so in covalent molecules. They can be used for ionic compounds though. So real quick, I'll start by showing you how to draw a Lewis structure for an ionic compound, and then the rest of this video will be dealing with covalent compounds. So let's say we have NaCl for an example. So we know when NaCl is formed, it happens by sodium becoming a positive ion and chlorine becoming a negative ion, meaning that sodium had to give one of its electrons to chlorine. So the Lewis symbol for sodium, Lewis symbols are going to basically show just the valence electrons around. So you just take the atomic symbol and put the number of valence electrons around. Sodium just has one valence electron. Chlorine has 7. Now remember, when you're putting valence electrons around an atom for a Lewis symbol, you basically go one at a time on each side. And then once each side of the atomic symbol gets a single one, then you can go back and start pairing them up. Alright, and remember, chlorine only has 7, so we stop there. So basically, this electron right here comes to fill chlorine's octet. Remember, that's why these ions form, to fill the octets of both of the atoms. So basically, the only way you'd have to draw this as a Lewis structure, you put sodium, you can put a +1 charge. You don't always have to put the charge there, but you can. Then in square brackets, you put the anion and show its full octet. And again, you can put a minus sign there. And that's basically how you're going to do it for ionic compounds. Covalent compounds, there's quite a bit more to it. So covalent compounds, you have to follow a certain number of steps. So the first step, you have to determine the number of valence electrons. And we're going to do a couple examples, so you'll see how to do that. But from that, you just get that from the periodic table. Then the second step, you need to draw the skeletal structure. The third step, determine what I refer to as the variable L. So determine L, and that is the number of electrons left to be put into structure. And again, as we start to do several examples, this will make a little bit more sense to you. After that, step 4, determine N. And N is the number of electrons needed to fill the remaining octets. And then lastly, step 5 varies a little bit depending on what these two L and N variables are. But basically, for right now, I'll just say compare L and N. And I'm going to show you, there's 3 different possibilities for what this last step will be, depending on what N and L are related to each other, relative to one another. And I'm going to show an example of all 3 of those. Okay, so to start, I'm going to start with the Lewis structure of CF4. So carbon tetrafluoride. So the first step, again, determine the number of valence electrons. And you get that from the periodic table. So basically just count along the row that atom's in. 1, 2, 3, 4. There's carbon. So carbon has 4 valence electrons. Fluorine, 1, 2, 3, 4, 5, 6, 7. Fluorine has 7. Right? So we just add up the number of valence electrons for every atom. There's one carbon atom. and there's 4 fluorine atoms. So we can say 4 plus 7 times 4. Again, 7. This 7 being the number of valence electrons in a fluorine atom, and there's 4 of them. So that gives us 32 electrons. So that's the total number of electrons between bonds and lone pairs that we need to put in our structure. So now the second step is drawing the skeletal structure. So that's basically where you just draw, you want to show the connectivity. So you just show what is bonded to what with one bond between everything. So the central, you always basically need to determine the central atom here. The central atom is always going to be the least electronegative atom, except for hydrogen, because hydrogen can only have one bond. And I'm going to touch on electronegativity in another video in this chapter, but basically fluorine is the most electronegative atom, and the further you get from fluorine, the less electronegative you are. So carbon is going to be your central atom here. So draw one bond to each of the fluorine atoms, right? And that's your skeletal structure. Now the third step, determine L. So however many electrons we need to put, we have left, to put into the structure. Now, so far we've drawn 4 bonds, and each bond has 2 electrons in it. So that means that we have used a total of 8 electrons already in our structure. So we can subtract that from the amount that we know we have to put in. 32 minus 8 gives us 24. So 24 equals L. That means that between bonds and lone pairs, we have 24 electrons that we still need to put into this structure somewhere. Now N. We need to determine the number of electrons needed to fill all of the remaining octets. Remember, an octet just means that in the valence shell, because all of the electrons that we're putting in the structure are valence electrons, in the valence shell, your atoms want a full 8 electrons. That makes them very comfortable and very happy. Carbon has 4 bonds on it. And again, each bond has 2 electrons, so carbon already has 8 electrons in its valence shell here. So it already has an octet, it doesn't need any more. Look, each fluorine has 1 bond right now, which means each fluorine currently has 2 electrons in its valence shell the way it's shown. So to get to an octet, if they already have 2, they need 6 more each. So each fluorine would need 6 more electrons to have a full octet. So 6 times 4 equals 24. So that's our N value here. Now we go to the last step. If N and L are equal, like they are here, all you have to do is fill the remaining octets with lone pairs. So again, each fluorine needs 6 electrons. So you have to put the electrons in pairs of 2. That's what I mean by a lone pair. So just give each fluorine atom 3 pairs of 2 electrons. And that's it. Now, for another example of what could happen in the last step, let's go with xenon tetrafluoride, XeF4. So again, step 1, determine the number of valence electrons. So now xenon is a noble gas. So that has 8 valence electrons. And again, fluorine has 7, but there's 4 of them. So that gives us 36 total electrons to put in. So now we can draw the skeletal structure, and the skeletal structure is going to start the exact same way here, because again, nothing's more electronegative than fluorine. So fluorine will never be a central atom. Alright, so now determine L. So once again, we put in 4 bonds. So that's 8 electrons. So we have 28 electrons left, and that's your L value. And N happens to be the same in this case, because xenon has 4 bonds, just like the carbon up here. So it has a full octet, and each fluorine currently has 1 bond to it, which means they would each need 6 more for an octet. So once again, N is 24. So if L is greater than N, so let's see, if L is greater than N, what you need to do is you need to give the central atom what is called an expanded octet. So basically, you can fill all of the remaining octets that you just determined. So each fluorine, once again, would get 3 pairs of electrons. And we just put in those 24 electrons. But if we subtract 24 from L, we still have 4 electrons left to put into our structure. Now, if L is greater than N, the extra, whatever electrons are left at this point now, so in this case 4, you have to put those on the central atom as lone pairs. So 1 lone pair there, 1 lone pair there. And if you're ever giving it more than, if you already have 4 bonds to the central atom, you need to put those diagonal to each other if you are putting 2 lone pairs on. And again, that's called an expanded octet. Now, one thing to keep in mind is that only the 3rd period and below are capable of having expanded octets. So if you're ever drawing a Lewis structure and you have something in the 2nd period, like carbon, nitrogen, oxygen, and you have that with an expanded octet, something got screwed up somewhere. Because expanded octets are only possible from the 3rd period and below. Obviously, xenon is below that. So this is your appropriate Lewis structure for xenon tetrafluoride. And now we do one last example here. We've already shown what happens when L and N are equal. Now we have L greater than N. So by process of elimination, this next one is going to be an example when N is greater than L. So for this, I'm going to do NO3 minus. And also, I want to show you this. Now, this is a charged, atom, so an ion, right? So when you determine the valence electrons, you can start the same way. Nitrogen, 1, 2, 3, 4, 5 valence electrons. Oxygen has 6, plus 6, but there's 3 of them. And then, whatever the charge is, you have to take that into account as well. So we have a -1, so that means that there's 1 extra electron. If it was a -3, there would be 3 extra electrons. And if it's a positive ion, we'd actually have to subtract that many electrons. So we have 24 total electrons here. 6 times 3 is 18, plus 5 is 23, plus this 1, 24 total electrons for our first step. Now, draw the skeletal structure. As I said for electronegativity, one way you can think about it is that the further you are from fluorine, the less electronegative you are. So nitrogen is further from fluorine. So that is going to be our central atom. Nitrogen. You can draw the 3 oxygens off of it. So now let's determine L. We have 3 bonds drawn. 3 bonds means 6 electrons. So we have 18 electrons left. Now let's look at N. So nitrogen currently has 3 bonds shown, as I said, which is 6 electrons, which means to get to an octet, to get to 8 electrons, it needs 2 more still. So let's see, N equals, so I'm going to say 2 there, plus, each oxygen has 1 bond shown, which means that each oxygen would need 6 more electrons to get to a full 8. So that's 6 times 3, 18. So N is 20. So if N is greater than L, you can plug them into this equation here. So you have N minus L divided by 2. So let's plug that in. So we have 20 minus 18. And again, keep that in parentheses because you want to do that first. Divided by 2. 20 minus 18 is 2. Divided by 2, which gives you 1. Now that number right there, that tells you how many extra bonds you need to put into your structure before you can fill the octets. So that means that you have to put in 1 extra bond. And so the extra bonds that you'd put in are in the form of double or triple bonds. So I basically need to put 1 more line. All of these oxygens are equal at this point, so it doesn't matter which one I put it on. I'm just going to draw 1 line there. That's what that 1 means. Now I can fill all the remaining octets. Nitrogen has a full octet now because I just gave it a 4th bond, so I don't have to do anything with nitrogen. This oxygen has 2 bonds, so that's 4 electrons, which means that it only needs 2 lone pairs to fill its octet. And these 2 electrons still only have 1 bond, which means they each need 3 pairs of electrons. And that's it. Sometimes, if you want, you can put this in square brackets and put the charge, but that isn't always necessary.